All right, how's it going, meteorology? I finally got this old lady's house set up with internet, so we are good to go. I want to pick back up where we left off, which was talking about air pressure and winds. One of the trickier things that we have to do here is really understand what we're looking at when we look at some of these different um, maps. So when we think about what we're looking at on a pressure map, what we have to kind of recognize here is that the values, these bars, or these lines that we're looking at, are corresponding to some other value. So maybe you're somewhat familiar with this idea of a topographic map. All right, so on a topographic map, you can take the you know, landscape, and then you have lines that correspond to different altitudes. So, where you see 1,000 meters above sea level, then that would correspond to one of these lines. If you have, lower, right, each of these lines would correspond to a different altitude. But you can look at these types of maps for anything, including, pressure and temperature. You can have contours of those things too, and we have already looked at some of those a little bit. So just like we could look at, say, for example, different altitudes, we could look at different pressures. So when we look at the surface pressure, then we can kind of relate these lines to area, like separating and showing us where we get higher and lower pressure. Um, now, we're not going to have one line for each possible pressure. We're not going to have one line for 1,000, one line for 1,001, but we do have very discrete intervals. Typically for the surface pressure, you can see here we're alternating between, there's a difference of 4 millibars between each of these lines. And so what we can understand then is that in between, say, this 1016 line and this 1020 line, we know that everything in between here is greater than 1016 in pressure and less than 1020 in pressure. So what you can do if you look at a map like this is basically start with either your highest or your lowest pressure. So we can say, all right, here's 1,003 millibars, right? So I can make a 1,004 line around here because I know that everything on the inside is less than 1,004. Everything on the outside is more than 1,004 until I get to the next line, which would be the 1,008 line. So now you can see this kind of goes around the 1,006. So inside is less than 1,008. And then outside is more than 1,008. And so you can make these contour lines, and basically this line represents a line of constant pressure, right? Everything here represents 10,016, but practically what you do is you go through and you say, well, if here's 1,008 and here's 1,019, yeah, 1,016 is going to be somewhere in between here, so I can kind of piece that together where those values are going to go, and now this is the contour map. Now here the pressures were increasing, right, until eventually I got to my highest point, and then they actually start decreasing again. You don't always just have, one particular localized, low and high. We can have multiple high pressures, multiple low pressures. Um, Now, the other tricky thing that we're going to be looking at is that, we're talking about the atmosphere at these different levels. So we do want to think about what's going on at the surface, but also recognize that what's going on at the upper levels is not the same exact picture. So you do look at different levels, the surface, the mid-level, the upper atmosphere, to get a picture of what's going on. And then once we have these kind of maps, we can also piece together what's going to be happening with our winds. So at the upper levels, it's a little bit trickier because as opposed to just measuring the pressure at the surface, well, as you go up in the atmosphere, you can see all pressures. And there are different ways that we can picture what's going on. We can either look at a certain altitude and then measure the pressure at that altitude. That's typically not what we do though, because altitude by itself can be very different when you're thinking about things like the topography underneath, where the actual ground level is. So instead of looking at altitude and doing different pressure, we actually will look at a certain pressure and then measure the height of where that pressure is recorded. So this surface, for example, well, this is constant pressure and constant altitude, right? Everything at 500, at 5,600 meters is exactly 500 millibars. We don't really observe that. Normally, we'll observe, right, a 500 millibar pressure at different altitudes. And like we talked about before, when the air is colder, then the air is going to be more dense, and I'll get to 500 millibars at a lower altitude than when the air is less dense and it's warmer. So now we can look at the 500 millibar surface, and that gives us an idea for what's going on with our pressure at the bottom um, and what kinds of winds we would expect in the upper atmosphere. So if we think about what's going on here, if our 500 millibar surface is at a high altitude, then we would, the contours here are not contours of pressure, but they're contours of the altitude. Um, there are contours almost more like a topographic map telling you that in this case, right, since the values are going down, it's like a downward slope, but we can also see those kinds of cutoffs, et cetera, et cetera. At the upper atmosphere, we typically don't see a lot of cutoff points, but what you will see are ridges and troughs. Maybe over a high pressure system, you might have a ridge up in the upper atmosphere. Over a lower pressure system, you'll end up with a trough up in the upper atmosphere. And then these troughs can, if you follow how they proceed, they might tell you a little bit something about storm development. Now, if we're looking at the surface, one thing we should already kind of know, and we talked about already, is that we typically get clockwise around high pressure system, counterclockwise around low. But now we're going to talk a little bit more about why that is. So for one, we know that pressure goes from high to low, or winds go from high to low pressure. That means that we should expect there to be a force that pushes our air from high to low, yet we don't observe a straight line wind due to pressure, and that's because there's some other forces that are going on here. Um, if we look at, the basic here, yeah, if we have high pressure and low pressure, if we have a higher, water level, that's going to be a higher tank or a higher pressure at the bottom, then we're going to expect that force to push the air from high to low pressure. And so that force is referred to as a pressure gradient force, right? The gradient is a difference in pressure from one point to another. And the stronger the pressure gradient, the stronger the pressure gradient force. But as you start moving the air, um, right, it'll experience some other forces. So if I have a cutoff, right, so basically the pressure gradient force is always going to kind of be perpendicular to these lines. Now where the lines are further apart means that the gradient is weaker. Where the lines are closer together means the gradient is stronger, and that would correspond to a stronger gradient force. So the other force that's really important for us to understand is the Coriolis force. I might have some videos that I'm going to try and post up which gives you some experience of this, but the fact is the Earth is rotating, and because the Earth is rotating, it means that um, when air starts moving, it's still got a little bit of that rotation. If you were on a normal merry-go-round and you push the ball from one side to the other, yeah, no big deal. You're going to observe that. Hold on, I just screwed something up. Anyway, you're going to observe the ball go in a straight line. But if you push the ball from one point to another while it's actually rotating, even as the ball moves, it's going to have this rotation. And from the point of view of this other guy, this ball is going to go veering off to the right. Even though it's actually still kind of going in a straight line. It just depends on what your point of view is. So um, because of this rotation, then when things move like air, it actually is going to, from our observation, have this rotation that goes with it. That's why in the northern hemisphere, when the winds start to move in a particular direction, they also tend to veer towards the right. That corresponds to um, that same cyclonic or anticyclonic rotation, if you think about it veering to the right. And planes have to deal with this too. They actually have to, if you just headed due east, you're actually going to end up with a more southward direction. Not until you're really on the equator does it not matter. And so the further north you go, the more exaggerated, or I guess the closer to the poles you go, the more exaggerated this Coriolis effect is. But the importance of the Coriolis effect for our winds is that, well, one, the Coriolis effect always acts towards the right of your air motion. And then the second thing is that the faster your winds are, the stronger your Coriolis effect is going to act. So what we can imagine here is if I have a pressure gradient force and I start with some air at rest, that air is going to slowly speed up in the direction of the pressure gradient force. But the more it speeds up, the more our Coriolis force is going to be acting towards the right. And so it's going to slowly turn this air until eventually the air is moving this way, and it stops speeding up or changing its direction because the forces are now canceling each other out. I've got the pressure gradient force, in this case, say to the north, and the Coriolis force is to the south. So those two forces are pulling against each other. Everything's balanced, and the wind is actually going to be perpendicular to both of those. Um, so this is why, the Coriolis force is a really big factor in why we end up with this rotation. And so, especially in the upper atmosphere, we see what we would call geostrophic winds. Basically, the winds are behaving exactly like this, where it's a balance between the pressure gradient and the Coriolis. And what that also means is when we see these pressure maps, we actually expect the motion of the winds to be more parallel. I think this video is about to be done recording, so